Okay, so what we're going to be going over today, guys, is mostly terminology, and then we're going to talk a little bit about why water does some of the weird things that it does, okay, and that'll be it. So it's kind of a short lesson, but it's also a short class, okay, so it kind of fits well together here. So terminology related to solubility. So we're learning a bit of vocabulary. We're going to learn some words and what they mean and how they apply. Okay. Understand what's meant by the term polar molecule. Okay. The term polar molecule is going to come up a lot in this course, both in this unit as well as in the biology unit. Okay. It's why we think that, basically that water is necessary for life to exist, because life basically harnesses the fact that water is a polar molecule and behaves in certain ways, okay, that other molecules don't. And then understand that because it is a polar molecule, water has many important and unique properties that make life on Earth possible. So we'll be looking at that as well. Okay? All right. Now, the degree to which something dissolves in something else is the definition of solubility. Okay? Solubility is a measure of how well or how much of something will dissolve in something else. That something else is often water. Okay? That's why we call water the universal solvent. Okay? It dissolves lots of things. Not everything, but lots of things. But that doesn't mean that it's always the solvent. Okay? For example, if you were painting like a fence with oil-based stain, okay, or a deck with oil-based stain, can you wash that off with soap and water? You can't. Okay? That oil-based stain is not soluble in water, which means it doesn't dissolve in water. So you have to use paint thinner instead, okay, or gasoline or diesel fuel. I would recommend paint thinner. It's less flammable, okay, but it's still flammable, but it's better to use that. Okay? That's because that stuff will dissolve in it, so it'll take it off really, really easily. Right? That's why some things come off really easily and some things don't. It's why we use like dish soap to wash greasy dishes. It's hard to get grease off of dishes with just water, because grease isn't soluble in water. But if we put soap in there, there's some surfactants and things like that in the soap that enable some of that stuff to now become soluble in the soap water solution that we create. Okay, that sort of makes sense? Okay. So, the degree to which something dissolves, that's solubility. A substance is said to be insoluble if it will not dissolve. Okay? So, like we were saying, stain, oil-based stain, is not soluble in water. Oil is not soluble in water. Gasoline is not soluble in water. Okay? They do not dissolve. Okay? But salt, sugar, alcohol, okay? Those kind of things, they are soluble in water. They dissolve. Okay? If I pour alcohol into water, does it disappear? Like visually anyway, obviously it's still there, okay? But I can't see the separation. If I pour oil into water, it separates right away. The oil floats on the top because it's not soluble. Okay? But if I pour rubbing alcohol into water, it just disappears because they are soluble in each other. Okay? It's why, alcohol can be mixed with other things in drinks. It dissolves in the other things. It just goes in. Okay? Does that sort of make sense to everybody? Unless you got something like eggnog or something that's really creamy, then it might float on the top. Okay, for the most part, if it's water-based, it's going to dissolve in it. It's possible for a liquid to dissolve in a liquid. It just means that they don't separate. All right, if a substance remains insoluble, then we call it a precipitate. Okay? And when we do our chemical reactions lab, maybe before the break, we'll see how we do. Okay? We'll have a couple of reactions where we'll take clear solutions, put them together, and we'll get a solvent. Okay? When we mix them together, something is created in the reaction that is not soluble in water. And as a result, it just suddenly appears as this solvent precipitates and falls out of the solution like snow. Okay? That's why we call it a precipitate. It falls out of the solution like precipitation and collects on the bottom. Okay. All right, so that's what we'll be seeing in this picture here. right? So two things were obviously mixed together, but one of them is not soluble, and it is going to slowly fall to the bottom, fall out of the solution, and collect on the bottom. All right, and I'll show you a little video of what that looks like here. Okay. All right, so a solution then is any mixture that contains a solute, that's the thing getting dissolved, dissolved in a solvent. The solvent is the thing doing the dissolving. Right? And we'll talk about that in a minute here. Okay, so a solution means that it is dissolved. A solution has one visible part. So Gatorade is a solution. Okay? There's sugar and electrolytes and things like that, and they're all dissolved in the water. There's no separation. Okay? It's a solution. Chicken noodle soup is not. Okay? Yes, there's lots of stuff dissolved in the broth, but there's noodles and vegetables that are not. Okay? Thus, it is not a solution. Okay. All right, so if we have a true solution, we also can call it a homogeneous mixture. Okay? Homogeneous means like one part. Okay? That's what the prefix homo means. Homo means one. Okay? Hetero means many, okay, or more than one. All right? Does everyone follow me there? Okay. So if I have something that is homogeneous, then it is all one part. Lots of things that we eat are homogenized. Okay? Like milk, for example. If you get milk straight from the cow and you leave it, it separates. Okay? There's a process called pasteurization that will homogenize the cream and the water into one part, and they will not separate. Okay? If you buy most non-organic peanut butter, or any kind of nut butter, almond butter, whatever, okay, it's homogenized. It's been made so that the oil stays in with the rest of the peanut stuff. Okay? But if you buy the organic stuff, it's not homogenized. And every time you open it up, there's a layer of oil on the top, and you have to stir it back in. Okay? It separates. So if something is homogeneous, it's all one part, and it stays that way. Okay? If you have something that has several parts, and they're forced together, I can mix them, but that doesn't make them a solution. They're only a solution if they'll stay together. Right? So I can take iron filings and sand and mix them together, but the iron doesn't dissolve in the sand, does it? Right? Like I can take a magnet and do this through the sand and come out and have all the filings on the magnet and have them separated. Right? I can't do that if I dissolve something in water. I can't just say, oh, well, I'll just pick them out again. They're in there now. The only way I could separate them would be to boil off the water. Okay? And then I take away the solvent. Okay? Is that making sense? Okay? So homogeneous mixture, all dissolved. Heterogeneous mixture is also sometimes called a mechanical mixture. Okay? So if I pour oil in water, it separates. But if I stir it really fast, I can get it to suspend in it temporarily, but it'll eventually separate again. That's a mechanical mixture. I can force them together, but I can't make one dissolve in the other. Okay. All right. Where do you suppose I might test this stuff? Could these be like easy quiz questions? Terminology, definitely, or multiple choice questions on a unit exam. That's usually where I test terminology and vocabulary. Okay, so which one of these pictures is the heterogeneous mixture?
The second one.
The second one, the one on the right. Okay, there's more than one visible part. One on the left, that's a homogeneous mixture or a true solution because it is in fact all dissolved. Okay. Okay. All right, so terminology here again. Solute is the substance that is being dissolved. Okay, and so if I have salt and water, salt is the solute. Okay, if I put sugar into coffee, sugar is the solute. It's the thing that's getting dissolved. And then the solvent is the thing doing the dissolving. Okay, so it's any substance that will dissolve another substance, which is why much of our like cleaning products, okay, like Mr. Clean or CLR or things like that, we call them solvents because they help us to dissolve things that wouldn't dissolve in water normally, right? I mean, could I get hard water scales off the inside of my shower just by scrubbing with water? Yes, but I'd have to do a lot of scrubbing. It's not so much that I'm getting it to dissolve in the water as I'm mechanically scraping it off, right? But if I take something like CLR, it will dissolve in that. That's a solvent. It'll take that stuff right off, and I have to expend very little effort, okay, to get it done. Okay, everyone clear on those two terms? All right, so a precipitate is any solid which is produced in a reaction and will not dissolve in the solution. Okay, so it stays out, right? So you can see it here in this picture as well. Right? There's obviously a solid that is formed and has fallen out of the solution and collected on the bottom. So I'll show you a quick video here, and you'll have to excuse, this video has the weirdest soundtrack. Okay, it's like mixing chemicals, but there's this like mournful Italian guitar music in the background. I don't know, it just it gives you like this weird vibe for what you're watching. So, precipitates are any solid that's formed as a result of either a reaction or something being dumped into something else and not being soluble. All right. Now, as we said before, solubility, the definition of solubility is the degree to which a substance will dissolve in another substance. Okay? That is how much of the solute can go into solution before it becomes saturated. Okay? Saturation means it can't hold anymore. Most of the time, we use that term when we're talking about, like, I'm so wet, I'm saturated, I couldn't possibly absorb any more water because I was out in a thunderstorm. Okay? But it actually just means that whatever it is, it can't hold anymore. So if you're like making like Kool-Aid or something like that, where you're adding sugar, okay, to water, if you're like me, I make it with warm water, and then I can get more sugar to dissolve. And then I put it in the fridge, and I know when I see the little line of sugar on the bottom that it's good. Okay, because I know then that the Kool-Aid is saturated with sugar and it can hold no more, right? And then it's nice and sweet and it's just right. Okay, that would mean it was saturated. It wasn't saturated when the water was warm, but as soon as I get the water cooled down, right, cold stuff can't hold as much as warm stuff, so some of it precipitates out. Okay, now some things should be soluble, and some things shouldn't be soluble. Okay? Case in point, the Twinkie. Okay? The original Twinkie was cake with like a butter cream filling. Okay? The modern Twinkie is like cake with something like buttercream filling. Okay? But the original Twinkie had a very short shelf life. After about a week, it wasn't any good. It would go moldy because it was full of natural ingredients like eggs and flour and sugar and butter and things like that. Things that are not generally soluble in water. So if you put a Twinkie, the original Twinkie, in a glass of water, it would just be like a sponge. It wouldn't dissolve, it would just suck up the water because it's cake. The modern Twinkie will almost entirely dissolve in water because we've substituted artificial ingredients for what used to be natural ingredients to increase the shelf life of the Twinkie, which is now up to like 6 months. Okay, so yeah, a Twinkie, like in lots of like post-apocalyptic movies, like joke is like, oh yeah, there's still Twinkies around. The Twinkies are still good because they're good forever. Okay, like there's some truth to that. Okay? If they're properly packaged, they have lots of things in them that are not, well, food. And so mold and bacteria don't really grow on them so much anymore. Okay? So instead of eggs, we have like an albumin. Albumin is an egg substitute that dissolves easily in water. Eggs don't. Okay? Eggs and water separate. Butter doesn't dissolve in water. But we've substituted for butter different types of oils, okay, and things like that. So it's like the difference between margarine and butter. Okay? They're not the same thing. They look the same. Beyond that, there's not much. They actually taste quite different. All right? And where do we get the yellow color from? The original Twinkie got it from the what? From the eggs, because eggs are yellow. The modern Twinkie doesn't have eggs in it. So they use yellow dye number 5, which is banned in most European countries as a known carcinogen. Okay? But we put it in because without it, the Twinkie would look like drywall. It would be gray because it gets the yellow color. It's supposed to get the yellow color from the eggs. Okay? So you put all these things in there, and you got a Twinkie that, well, if you had your jaw wired shut, you could still eat. Because you could put it in water and then eat it with a straw in a little bit of time. That's after a little bit of time, that's what it would look like. Okay? It would be almost entirely dissolved, okay, in solution because of that. All right, so yeah, the Twinkies changed quite a bit. A lot of it was just like during World War II, they couldn't get a lot of the natural ingredients anymore. Okay, so they went to like a strawberry filling for a while, and then they went back to the cream filling and all that. But yeah, it went through a lot of changes over time to be more marketable and more profitable. Okay, so, I'm totally not that person. Like, you got to eat all organic food because I eat crap too. Okay, but yeah, you should really know what's in your food. That shouldn't dissolve in water. Cake shouldn't be soluble in water. All right. Now, can some things affect the solubility? We already know temperature can affect solubility, right? The hotter it is, the more of it will dissolve. Can anything else? If you want something to dissolve, what's your natural reaction to do with it? Stir it or shake it, agitate it in some way. Okay? If you get the particles moving, the spaces between them become more readily available for things to dissolve in, so they're going to dissolve more easily. Okay? So if you put something in a bottle, you can quickly shake it and get it to dissolve better than if you just left it there. Okay? Because the agitation results in the molecules moving around and things being more soluble. Okay. On the back of your periodic table, can everybody take that up? Because we've got to learn how to use the solubility chart on the back of our periodic table. Okay, so it's important to be able to tell whether something is soluble in water or not. Okay, because most of the time we're dealing with things dissolving in water. So this chart allows us to do that. The way the chart is set up is that all of our negatively charged ions are in the top row. Okay, at least common ones are in the top row. And then our positively charged ions, the metals basically, are in the next 2 rows. If something is in this second row, then it's soluble with whatever's above it. If it's in the third row, it's not soluble with whatever is up here on the first row. Okay, so if I'm looking at, let's say, sodium fluoride, let's say. Okay, so sodium fluoride would be NaF. So if I want to figure out if this is soluble, I look for fluorine, which is right here, and then I go down below it. It says it's soluble with most things, which is like the least helpful thing that could possibly be written in that box, but that's what's there. Okay? So it's soluble with most things. So then what I got to do is say, okay, it's not soluble with these things, and I don't see sodium there. So sodium must be part of most, and then this would be soluble. Right? But if I had this, lead 2 iodide, right? I would go and I'd find iodine. Okay, so it's right here. It says it's soluble with most things. Yay. Okay. And then I go down here and it's not soluble with copper, silver, 2+ mercury, or 2+ lead. Soluble or not soluble? Not soluble. All right, so if the metal appears in the bottom row, that compound's not soluble. If the metal appears in the middle row, that compound is soluble. Everybody with me? Okay, do the ones I have listed there. Just write S or NS beside them. Give you a couple minutes to get ahead of me and then we'll go through those ones. All right, so our first one, we got calcium sulfate, which is CaSO4. All right, so we go up top, we look for SO4. SO4 is right here. Okay, it says it's soluble with most things, but calcium is the first thing listed in the bottom row, which means that stuff is not soluble. Okay. Potassium hydroxide. All right, so hydroxide, so we're going to have KOH for that. Hydroxide's right here. It says it's soluble with group 1 ions. Does that include potassium? Well, here's potassium. Is it in group 1? Then it's soluble. Okay, so when it says group 1 ions, it's talking about the number on the column of the periodic table. Okay, so group 1 is the first column. All right, so that one is soluble, okay, and lead 2 chloride. So we'd be looking at PbCl2. All right, so we find chlorine. Chlorine's right here, so this is going to be the same as the one we just did. Okay, so chlorine soluble with most things, but lead is right here in the not soluble row, so that one would be not soluble. Tin 4 fluoride, SnF4. Okay, so we are looking for fluorine. Fluorine's right here, soluble with most things, but not lithium, magnesium, calcium, strontium, barium, lead, or iron, lead, and mercury. Well, I guess it's soluble then, because tin is not listed down in that row. All right, then we got copper 2 sulfate. That would be CuSO4. Okay, so with sulfate's right here, soluble with most things. I don't see copper listed in the bottom row, so that stuff is soluble. Okay, we got potassium bromide, so bromine's right here, soluble with most things. I don't see potassium listed in the not soluble group, so it's soluble. Okay. Silver fluoride, so fluorine's right here, soluble with most things, and I don't see silver listed in the not solubles, so that one is soluble. Okay, and lastly, beryllium nitrate. Okay, so nitrate is right here, right? Soluble with most things, and beryllium is not here, so soluble. In fact, almost all nitrates are soluble. Nitrate is just one of those ions that makes things happy to dissolve. Okay. All right, questions on how that works? Okay, so here's how I would ask stuff about this. I could have a multiple choice question on a unit exam that says, which of the following is soluble, and you'd have to look them up on your solubility chart and do what we just did. Or you could have a lab, let's say the reactions lab, where you have to determine which of the products was the precipitate, because you're going to have 2 reactions that are going to form precipitates, and you're going to have to figure out which one of them was the one that didn't dissolve using your solubility chart. Okay? All right. Questions on the solubility chart or anything to do with solubility? All right, that's all we're going to cover with solubility. All right, now talking about water and the polar nature of water. Okay, so atoms can come together and form compounds. Okay, we know that that's part of Dalton's atomic theory. They can have ionic bonds if it's a metal and a non-metal, or they can have covalent bonds if they're both nonmetals. In those covalent bonds, we talked about how the atoms share their electrons. But the sharing implies they share equally. But that is not true. In very few covalent bonds is the sharing of the electrons actually perfectly equal. Okay? And the reason for that is some elements are more electronegative than others. Okay? And electronegativity is one of the things that's listed in each element's box on the periodic table. It's this little number here underneath the atomic number. So hydrogen has an electronegativity of 2.2, which isn't bad. Okay? Like it's not the lowest of the low. Okay? But oxygen has one of the highest electronegativities at 3.4. So it's much more electronegative than hydrogen is. What electronegativity means is how hard do you hold on to electrons? Okay? The higher that number, the harder you hold on to them when you get them. So when water and hydrogen bond together, when oxygen and water bond together to when oxygen and hydrogen bond together to form water, I said it right that time. Okay, the sharing of the electrons isn't equal. These electrons spend way more time down here than they do up here. In fact, so much so that they don't really orbit like this anymore. They spend their time like this, around oxygen, much more. They still get close to the proton in the nucleus of the hydrogen atom, but they don't spend much time above it. And what that leads to is essentially two protons that are exposed at the top of this molecule. And what charge do protons have? They're positive. Okay? The other part of this is that the negatives hang out more down here. And so what we end up getting is a positive pole, actually two positive poles, and two negative poles on this molecule. Okay? That's why we call it a polar molecule. It means that the ends are charged, and they're charged opposite. Okay? So that can lead to some of the behaviors that we see water exhibit that other other molecules do not. Okay? Like, for example, can you fill a glass slightly more than full with water? Why? What's that called when it goes over the top? Surface tension, yeah. Okay? Surface tension, or a meniscus is what it's technically called, okay, is the result of water molecules actually forming hydrogen bonds with each other. And the reason they do that is because if I've got this water molecule here, okay, it's kind of shaped like Mickey Mouse, right? This end is positive, this end is positive, this end is negative, this end is negative. Well, another water molecule over here with its positive end is attracted to the negative end of this one. And they'll form a weak bond between them that holds those two water molecules together. These bonds are not very strong. Like, I mean, all you have to do is poke the meniscus and the surface tension is gone and it's all over, okay? But there's a bond there that can form and break and reform very, very easily, okay? That's the result of water being a polar molecule. It's also why if you fill up a glass, like with really, really cold liquid, you'll see water condense on the outside of the glass, but the droplets will stick. Right? They'll stick to the outside, and until they get too big, they won't run down. When they get big, they'll run down. Okay? They're actually forming a hydrogen bond to the glass. Okay? There's a part of the glass that's charged. The water molecule forms a hydrogen bond with it, and it'll stick to it until it becomes too heavy for that hydrogen bond to hold, and then it'll run down the glass. Okay? Or why we see water bead up on the, like if you just waxed your car, or if you look on like the surface of a leaf that has wax on it, the water will bead and it'll sit there until the bead gets too big and then it'll run off. It forms a hydrogen bond with the waxy part of the leaf or the wax that you put on the car. It'll form a hydrogen bond to that and it won't penetrate. It'll sit on the surface until it becomes too heavy for those hydrogen bonds to hold and then it'll fall. Right? This is also how part of how plants transport water. Okay? Plants can transport water. If it's like a giant sequoia, we're talking hundreds of meters, okay, from the bottom to the top, right? And they do that without any energy. They don't use any energy to do it because they have tiny little tubes inside the stems that have water in them, okay? And that water forms hydrogen bonds with the inside of the tubes and with itself. And essentially, anyone ever play with a barrel of monkeys when you were a kid? You know, the monkeys, you can hook their arms together. That's kind of what happens with the water molecules going up the trunk of a tree. They will hydrogen bond to each other, like linking the monkeys together, okay? Or they'll hydrogen bond to the inside of the tree, just like sticking it against the side. It'll adhere to the inside of the tree because of these hydrogen bonds. Okay? So that's some of those weird things that water does that other molecules don't do. Okay? If I was to try and fill up a glass with just rubbing alcohol, I wouldn't get that surface tension because rubbing alcohol isn't a polar molecule. Once I got to the top, it'll just start running over. Okay? It won't form a meniscus. It won't form surface tension. It doesn't do that because it doesn't have charged ends that can bond to other things. Okay? Is that sort of making sense? Okay, so here's what you need to know about a polar molecule. Okay? A polar molecule is caused because the electrons are not shared equally. is polar if it doesn't share the electrons equally. Okay, and if it doesn't share the electrons equally, then it can hydrogen bond to other polar molecules or to itself. What's something else water does that other things don't? Yeah, when it freezes, what does it do? It expands. Almost nothing else does that. Okay? Most things, when they go from their liquid form to their solid form, contract. Okay? Water expands. We all know that. We've all broken something in the freezer where you put the plastic water bottle in, and then when you pull it out, it can't stand up because the bottom's pushed out. Okay? Because the water expands when it freezes. And that's, again, because water is polar. So, as the water gets colder, it contracts as a liquid. It contracts. But it gets to a point where you're forcing these charged ends closer and closer together. So that's fine when it's a positive end and a negative end. They want to come together. But the closer you get these, the closer the negative ends get to each other as well. And there comes a point where it's like you're pushing on a spring. Okay? And you're pushing and pushing, and eventually it just gets to the point where you can't hold it anymore, and you let it go, and it bounces back. Okay? That happens right at the freezing point. Water actually takes up the least amount of space at about 4 degrees Celsius. It starts to expand colder than that. Okay? And so when it freezes, okay, they're getting closer and closer together, and then when it freezes, they pop apart right at the last second. Okay? And that water expands outwards as it freezes. Okay? Now, that's actually really important for a lot of things that live in cold water. If water didn't expand when it freezes, where would lakes freeze from? Okay, or let me ask you this. If you put ice cubes in water, where do they go? They go to the top because they're less dense than the liquid. That is rare. If I had like a chunk of solid mercury and I dropped it into a liquid mercury, it would sink to the bottom. Almost everything else in its solid form is more dense than its liquid form. Water is an exception. If water wasn't less dense as ice than it is as a liquid, lakes would freeze from the bottom. Which would mean then that they would freeze solid all the way from top to bottom. But because ice is less dense than water, they freeze from the top, and you get a barrier between the cold outside air and the liquid, and lakes won't freeze all the way to the bottom, which means the life in them doesn't die over the winter, okay? Because some of the water remains liquid. Make sense? So all of these are like things that water does that is unusual, okay? Because it's a polar molecule that make life on Earth possible. Okay, so we talked about that. Okay, and this is what I was just talking about with water as it freezes. Okay, so liquid water, the water molecules are really close together, but as a crystalline solid, as ice, okay, the crystalline structure actually has the water molecules further apart because of that repulsion. Okay. Now, a hydrogen bond can form between any two polar molecules. It can be water to water, or it can be water to ammonia, or water to any other polar molecule. Okay? They have different names, though. If water bonds to itself with a hydrogen bond, we call it cohesion. Okay? So a hydrogen bond, water to water, is cohesion because they're alike. Okay. If it bonds to something else, like in this case, this is called adhesion. Okay. Because an adhesive puts two things that are not alike together. Okay. So the process of adhesion means to stick two things together. Cohesion means to stick like things together. So as I was saying, this is how a tree is able to transport water from its roots to its leaves, sometimes over 100 meters or more. Okay? As the water evaporates out of the leaves, it's hydrogen bonded to other water molecules that are lower down. Okay? So like the barrel of monkeys, as one water molecule leaves the leaf, it pulls on the ones below it through those hydrogen bonds. Okay? And it can lift them up into the higher points of these tubes. Okay? Now, the way for that to work is that the tubes have to be really, really small, like microscopic. Right? So there aren't like big straws inside the stem of a tree or the trunk of a tree or even the stem of a small plant. The tubes, called xylem tubes, are microscopic. That means then that there's not that much water in each tube, but there are lots of tubes. Okay? Because if I had just a big like pipe, okay, full of water, is the mass of the water fairly great? Right? Water's pretty heavy. So if I have just a big tube, there's a whole bunch of water in the middle of that tube that's not supported. Okay? The water has to be able to bond to the inside of the tube as well as to itself. If I've got a whole bunch of water that can't touch the edges of the tube, then it can only bond to itself, and that's going to be too heavy. The hydrogen bonds aren't that strong, and it would fall back down. Okay? You can kind of investigate this yourself. Get a really small straw and one of those big fat slurpy straws, okay, and try and drink the same thing through them. Right? It's really easy to pull liquid up through the smaller one, but you have to pull harder to get stuff to come up the bigger one because there's more liquid in it, okay, and it's heavier. Right? In the small straw, there's not that much liquid in it, so it's easy to pull it out. All right, so you've got those two processes we just talked about, cohesion and adhesion, going on inside these tubes. Okay, so if we kind of blow it up here, each one of these is a water molecule, right? So we got adhesion, a hydrogen bond to the inside of the tree, and we got cohesion, hydrogen bond to water, okay, holding it up, right? And not very big tubes, so we can pull lots and lots of water up the tree as a result. Okay. All right, and then we also talked about surface tension, which is the same thing. It's cohesion. It's water molecules that are hydrogen bonded to each other, and it creates essentially a layer on top of the water. Are there organisms that use that to their advantage? Totally. Okay. Any bug that can sit on the surface of water is using that to its advantage. Okay. And there are lots of bugs that sit on the surface film, okay, in lakes and rivers. Okay, they're food for fish. Right? They sit on the surface, fish come up and eat them. Right? If you've ever done fly fishing, that's how the whole thing works. Okay, you make things that'll sit on the surface and look like real bugs. Okay? But they have to sit in that meniscus, okay, that surface film, which means they can't be big and heavy, or they'll break the hydrogen bonds and they'll fall through. Okay, or they got to move really fast, like the Jesus lizard. Okay, if you guys have ever seen that thing, but it just runs across the surface of the water. Okay, its legs are just like going like this. Okay, and it can get across because it's moving really fast. It kind of breaks that surface tension, but it's moving fast enough that as it breaks, it's propelling forward and stepping on a new spot. Okay, it's different than buoyancy. All right, buoyancy is when something will float on the water. That's not sitting in the surface film. It's just shaped right, or it's not very dense, and it'll actually literally float. Okay, so don't get the idea that buoyancy and surface tension are the same thing. They're not quite the same thing. All right, is that making sense? Okay, so things we need to know. What's a polar molecule? So unequal distribution of electrons, charged ends, hydrogen bonds can form, cohesion and adhesion. Okay, so cohesion between the water molecules, adhesion is water to something else. Okay, and then some examples of where it gets used. Surface tension, bugs sitting on the surface, plants transporting water. Okay, that's the kind of thing we got to know. Okay, what do we got here? 25. Okay, we got 3 minutes. Good time. Okay, reminder, your lab reports are due on the 15th of next week. Right? I will not be here on Monday. Mr. Van Earth will be here for me. And he's going to go over the lesson on chemical reactions, introducing chemical reactions to you guys, and then we'll go over that in more detail on Tuesday. If you want to come in and ask about your labs, come and see me on Tuesday or Wednesday. Okay? and we can go over those if you want. Okay, come see me either at lunch or nighttime or right after school, and I can look over it. Okay? Have a good weekend, you guys. But not too good.